Okay, so there's one last idea that I want to discuss, and that is the fact that faster than light communication spoils relativistic causality. Okay, so let's see if we can prove that. Okay, so let's again draw a space-time diagram. So this is going to be T, and let's make this X. So there's X, there's T. And now I would like to draw on some lines of constant time. So all of these thinner lines here, all of these points have some constant time, okay? So the thick line, the x-axis, this could be t is equal to 0. The next line, t is equal to 1, t is equal to 2, t is equal to 3, and so on. And we can also draw some lines for some negative values of t. Good. And what I'm also going to do is I'm going to draw on a second frame. And the second frame is obtained by doing a Lorentz transformation. So I boost to get to the second frame. So this is t primed. That is x primed. And I again want to draw lines, but now of constant t prime. Okay, so the x prime axis t prime is equal to 0. This is maybe t prime is equal to 1. T prime is equal to 2. T prime is equal to 3. This is t prime is equal to -1, and so on. Okay. And now let's imagine the following. So this is u. Okay. Oh, let me change that. This is you. And you are going to send a signal. Okay. And you will send a signal to this point over here. So this is A. That's B. So let's imagine the following. You are happy. So you send a signal from A at, so where is A? A is at t is equal to 0 to me at B. And at B, well, I'm on this thin black line. I am at t is equal to 1. That's the cause. So this is the cause. So the cause is at t is equal to 0. I read your message and get happy too. That is the effect. I get happy. And this happens at t is equal to 1. Okay, along this thin black line. Super. So there's the cause at t is equal to 0, and at some point in the future, there's the effect at t is equal to 1. Now, let's look at things from the point of view of the red frame. Well, A is on the thick red line, so the cause is at t prime is equal to 0. So the cause is that T prime is equal to naught. The effect, that's me at B, well, that's the thin red line. But that comes before the thick red line. So the effect is that T is equal to -1. So in the red frame, at T is equal to -1, I get happy because I'm reading your message. And then at T is equal to naught, at a later time, you send the message. So in the red frame, the effect comes before the cause, which means we have spoiled causality. The effect comes before the cause. We have spoiled causality. Now, why actually did this happen? How do we prevent this from happening? Well, let me tell you how we prevent it from happening. So, if this is T and this is X, there is T and this is X. Remember, there's one thing that all Lorentz observers agree on, and that's the speed of light. So if I put in the speed of light here, there it is. Inside the red frame, inside the primed frame, so this is T primed, and that's X prime. And what you can see is this blue line is exactly halfway between T and X, and it's also exactly halfway between T prime and X prime. And this is the statement. You know, the reason why we scissor about this blue line is because we both agree that the blue line is the world line of light. All Lorentz observers will agree with that. And if I require that, so, oh, sorry, let's change color. If I require that the effect is time-like separated in the Tx frame, comma, then it is time-like separated in the T prime X prime frame. Okay, so let's maybe say that that's the cause. This is the effect. It's obvious. Look at the TX frame. It lies above the blue curve, so it's inside the light cone. The effect is inside the light cone of the cause. But look at the primed frame. It's also inside the light cone in the primed frame, because it's also above this blue line. The blue line is the thing that hasn't changed. So if I require that the effect is time-like separated from the cause in one Lorentz frame, then it's time-like separated from the cause in all Lorentz frames. And another way, purely mathematical way to see, of course, that that's the case, is that the statement that you are time-like separated is the statement that y mu is greater than 0. But you know that y mu is a Lorentz invariant because it's a contraction of a 4-vector, and that is Lorentz invariant. So the correct way to put in causality in a relativistic theory is to say that the effect must be time-like separated from the cause. Okay, so I should say effect and cause. Effect and cause are time-like separated in Tx frame, then they are time-like separated in the T prime X prime frame too. So faster than light communication spoils relativistic causality. And as our final statement of this chapter, of this section, we can say relativistic causality requires the effect is time-like, separated from the cause. Okay, so this is now everything that we wanted for this chapter. So we're discussing observables in a special relativistic quantum theory. Special relativity forces observables to be fields. Quantum mechanics forces observables to be operators. So in quantum field theory, observables must be operator-valued fields. We also know that space-like separated operators must commute. We also know that faster-than-light communication spoils relativistic causality, and that relativistic causality requires that the effect is always time-like separated from the cause. And that completes this chapter.